Hey everyone, my name's Tyler. I am a fourth year undergraduate physics student at the University of Guelph, and I am very excited because I get to talk to you, the viewer, about two of my favorite things today. I get to talk about baseball and two, physics. That's right, today I'm going to talk to you all about how to use physics to judge a fly ball in baseball. For those of you that aren't too familiar with the great sport of baseball, typically when a ball is hit at a high angle, it travels through the air and we have an outfielder who their goal is they want to try and catch that ball. How they do that is they move through their horizontal plane so they can get themselves underneath that ball in order to best position themselves for a great spot to catch it. Okay, cool. So what does our outfielder need to look at in order to know where the ball is going to end up? To get a better understanding of what's going on, let's take a zoomed in look at our baseball here. We know it's being hit with some initial speed, or exit velocity as we'll call it. We'll denote this with V0. We also know that it's coming off of the bat at some angle relative to the horizontal plane. We will call this angle theta. There's some other things acting on this ball as well. We know that gravity is going to be constantly pulling that ball downwards at a constant rate. We also can assume some things about the weather. Maybe some wind might push against our ball. We also know the ball might spin, and with that, it could have some movement as well. Another factor would even be air resistance. However, for the scope of this, we are going to neglect first these more complicated issues and just focus really on the legs of the equation. Now, we call these the legs of our equation because they're going to do the heavy lifting for us. They're going to be doing the heavy lifting in our equation called range. Our range on screen here is what's going to help us determine how far in the horizontal plane our baseball is hit, relying on only two initial conditions, our exit velocity and our launch angle. We also will use gravity in our equation, but this is a constant near Earth's surface, so we don't have to worry about this being a changing variable. All right, but that's just math. What does it actually look like? Well, on screen here is an example of what it would look like if we were to hold our launch angle constant but vary different speeds of different exit velocities. This isn't anything too curious. It makes sense that the harder you hit a ball at the same angle, the farther that ball is going to travel. Things look a little more different when we consider a fixed velocity and a changing launch angle. However, when you begin to look at it for a bit longer, you start to realize that something hit at a more shallower angle just doesn't have the air time to go as far. And something hit at too high an angle just doesn't have that horizontal movement to go as far either. And it makes a bit more sense that the most optimal angle would be somewhere in between, where you're getting a good mix of air time as well as horizontal movement. But what's really important to remember is that launch angle and exit velocity work together to give us our range. This can result in multiple different types of flight paths that give us multiple different ranges. Sometimes optimal angles give us a great range. Other times non-optimal angles can be overshunned by a overpowering exit velocity. Now, if you remember from earlier, we had a couple terms from reality that we disregarded. And I was wondering, how accurate is our range equation without these non-legged variables really? So I decided to go and test it. So my production crew and I hit the field and made our own guesses.
I think that the projection is going to be like 60% accurate.
It's gonna be about 80% accurate.
18% accurate.
67% accurate.
I think it's going to be 85% accurate. Following our predictions, we wasted no time at all.
Go.
When the ball was caught, we got right to analyzing the footage to find our launch angle. This also allowed us to get our exit velocity by using the frames per second to calculate the speed off the bat. From this, we got an exit velocity of 30 meters per second. We plugged this and our angle of 22 degrees into our range equation. This gave us our range value of 63.73 meters. With measuring the distance we found the ball to land at, we found it to be
Is 50.75 meters.
This ended up being about 20% short of what we were expecting and gave Andrew the win.
That means Andrew is our winner.
All right, so we found it wasn't perfect, but we did find it to be within 80% accurate, which is pretty awesome given that we only had 2 variables to work with. Overall, the range equation was pretty accurate in predicting reality, so I would say that in the terms of judging a fly ball, maybe it's not perfect, but you're 80% of the way there. Thank you very much for watching.